Morning, everyone. So yesterday we started to take a look at how we would go from Lewis structures and apply a very simple principle called VSEPR. VSEPR again uses the idea that around every central atom there are places that are negative. We call them electron domains. Depending on how many places are negative, those domains will always push each other far away. They're going to maximize the bond angle, so therefore the repulsion between the electron domains is the smallest it can be. So far in this chapter here, as I mentioned, you will always need to start off with the Lewis diagram. Lewis does not care the geometry. It just wants to make sure that you have a correct tally of all the valence electrons, that everyone has a full octet, except for the exceptions that we saw in a previous lesson. And then, as I mentioned here, we're going to then start applying VSEPRs. There were a lot of different names for the different geometries. You will need to know those names. You need to know the angles, and you also need to know how to draw those ones in 3D. So make sure you get some practice using the wedges and dash notation. Today we're going to continue on further. This chapter here is fairly theory heavy at the beginning. So what's going to happen here is we're going to find that VSEPR, it predicted for us quite a few shapes. It predicted for us things like tetrahedral. You should be able to remind me, tetrahedral here has bond angles, say 109.5, trigonal planar, so let's just say triplanar, 120 degrees. Using that really easy idea, it does actually match up with real life. Because the domains are pushing each other away, they have access to 3D space, we end up getting these really fantastic geometries. Turns out when we just compare it back to stuff we learned from chapter 2, chapter 3, we realize that our previous, we can call it modern quantum theory or SPDF kind of theory here, turns out the VSEPR doesn't really jive well with SPDF. For example here, s orbitals, if you just drew them out here on a 3D plane here, s orbitals are spherically symmetric, right? So this one here really doesn't give us any variety in terms of bond angles. As you start looking at the p orbitals, do make sure you know that the p orbitals are dumbbell shape. But if you can remember for yourself here, these p orbitals here, although there's going to be 3 of them on any energy floor, it's always going to be at, say, 90 degrees from each other. And because it's at 90 degrees from each other here, I can explain bond angles of 90, so octahedral, no problem, ligands coming around a central metal, no problem, but I cannot come and explain to you how is the bond angle here bigger than 190, it's at 109.5 or 120, something isn't jiving well between these two. So it's nothing wrong with either theory. We saw that SPDF made good predictions. VSEPR also makes good predictions. What we're going to do today is a lesson on hybridization. We just want to bring these two models together. We want to make them consistent. And with this newer model, we want to see what other predictions that this one here makes for you. So between VSEPR and SPDF, the thing that's going to bring them together is our theory on hybridization. And then we're going to step through in this lesson here, what is this hybridization, see how it fixes our problem, as well as make some new predictions. So we're going to start off here just looking at hybridization. Our first example is the molecule methane. We're going to do a quick crash course on naming organic compounds later on. You're going to see that a parent name that actually starts with something meth means that it implies that there's one carbon in the structure. In this case here, the ending of it, this is called the suffix. The suffix is in the alkane family. Alkane means everything is single bonded. Next year, we're going to do an entire chapter on this one here, the naming, the reactions. It gets very fancy, but for the time being, if you can use these little hints for yourself, oh, meth means 1, we're going to see ethane later on, eth means 2, it might actually help you in drawing the pictures a little bit easier. So with that said here, let's start off with methane. We have our carbon. I would expect hydrogen to be terminal. Hydrogen has an incomplete octet. It's a smaller shell. It can only have 2 electrons. The carbon here having 1 central atom here. It's in group number 14, so we know from Lewis it has 4 valence electrons. Remember, Lewis does not care the geometry, so unless I actually ask you draw the 3D diagram, draw it however you like. Normally, we like looking at symmetrical pictures because symmetry usually is what's represented in real life. But again, as I mentioned, Lewis does not care the geometry. You can put all the hydrogens on one side. It's still a correct Lewis diagram as long as everyone has a full octet. So this one here is methane. We did this in the VSEPR lesson yesterday. You can talk about VSEPR first. So around 1 center at a time, this methane here happens to have 4 domains. When 4 balloons push each other away, we saw that we're not stuck to a flat plane. In fact, this one here will push each other, tie 4 balloons together. You're going to naturally get this orientation of that tetrahedral geometry. And that's what I mentioned here. The bond angle is going to be 109.5. That's the maximum that bond angle can be. And yet our SPDF stuff here, I have no orbitals that are actually at 109.5. So what we need to do is we need to do a fix of this. There's also one other problem that's not super obvious here. If I try to do the electron configuration for carbon, you would say carbon, 1s2, 2s2, 2p2. If you actually look at the energy level diagram, the 2s is lower energy here. There's 2 that's filled up. The 2p's come in sets of 3, and I have 2 that are unpaired like that. In this diagram, based on our Bohr, based on our Lewis, it's correct. Again, even though technically the first 2 should be shared, we actually see that carbon ends up making 4 bonds. Now, we've been used to seeing bonding from covalent bond is made out of 2 electrons. 1 electron comes from each neighbor. I see that carbon at least has 2 unpaired electrons. I can explain 2 out of these 4, when in reality, the S's, because they're lower energy and as they're off-ball, these 2 should actually be paired up. They actually shouldn't actually be unpaired electrons like this. Carbon shouldn't actually be able to make 4 bonds. Now, we have seen a special type of bonding in Chapter 3. Well, it is possible that sometimes you can have things that have lone pairs. They can be so generous, they can donate both electrons in the bond. We refer to those as coordinate bonds. But even in that case there, if that happens, I make 2 bonds with the unpaired electrons. I can make 1 data bond or 1 coordinate bond potentially. That's going to become 3 bonds. I still can't explain the 4th bond. So all this to show you here, not that Vesper is wrong, but it's inconsistent with what we've been knowing previously. How we're going to fix it in today's lesson here is we're actually going to, like as I mentioned, use hybridization. Here's what's going to happen. We're going to start off promoting the electron from S to P. Now, back when we were doing electron configuration, we would always do ground state. We would always go lowest energy first, pack up any lower shells. It's more stable. In this case here, because carbon is known to make 4 bonds really naturally, let's pay a little bit and let's put this electron up top. Yes, I get a little bit back for having a half-filled shell, but this is probably going to be endothermic. I had to chip in a little bit. What does that help me do? Because I promoted the S electron up into the P, at least I'm going to end up with 4 unpaired electrons. So at least I can then say, that's how carbon ends up making 4 bonds. Then another problem arises here. Sure, you do have the capacity to make 4 bonds here. If 3 of the bonds are with S, S's are spherically symmetric here. 3 of the bonds will be some way. I don't really know the bond angles. But if one of them is one of them is at S, 3 of them are with P's, one of them will look different from the other 3. So the S's are going to be spherically symmetric. The p orbital ones here should be 90 degrees. They shouldn't be 109.5. So here's what's going to happen, and here's how we're going to solve the mystery. How do we explain not only carbon making 4 bonds? When we look at this in real life, the 4 bonds are actually completely identical, and let alone the bond angle is actually bigger. Our notion of hybridization, you're going to look at the center one at a time, just like Vesper looks at center one at a time. Before we actually look at our actual, these are called atomic orbitals, because these are carbon's orbitals by itself. Carbon had on energy level 2, 1 s orbital and 3 p orbitals. Before carbon actually tries to bond with hydrogen, carbon actually hybridizes. It makes a blend. It trades in this s and the p orbitals, and it blends them together to get some hybrid orbitals or blended orbitals. Those blended orbitals here will have energy that's somewhere in between. So the s orbital is low energy, the p orbital is high energy. There's a lot of math behind the scenes. We don't need to do the math, fortunately for us. But a lot of the math behind the scenes, we end up something intermediate in energy. We end up with 4 orbitals. These 4 orbitals here are what are called degenerate. They're all equal energy. So degenerate, equal energy. Your study guide likes saying, of lower energy. In fact, it's not lower energy. The overall energy shouldn't change. All I'm doing is I'm mixing my S and my P. Sure, my S's were lower energy, my P's are higher energy. I prefer the language of the energy reading here is somewhere intermediate in energy, somewhere in between. Because of energy conservation, it may not be as energetic as just the individual p orbitals or low energy as the s orbital, but somewhere in between. So that's what hybridization is here. Essentially what the math behind the scenes, remember there's a wave function, there's an equation, looks like a pitchfork here. This one here actually is an equation that describes the orbitals themselves. So this wave function here for the 2s orbital, this is the wave function here for the 2px, 2py, similarly. Again, the math behind the scenes starts taking these equations and start mixing these orbitals together. Again, lots of math behind the scenes. You don't need to see that math. And we end up with this hybrid orbital. We end up with hybrid orbitals because I traded in 4 orbitals in total. I always expect to get 4 out. This always comes out from the math. However much I trade in is exactly the number of orbitals I get out. And the other thing here is you'll notice the name of this orbital. Sure, we're all on energy level 2. I don't really care about 2 sp3 or 3 sp3 or whatever. I'm just going to care about what blend have I made it. Because I've traded in a single s and 3 p orbitals, I'm going to call it an sp3 orbital. I've traded in 4 orbitals. 1 of them was the s kind, 3 of them were the p kinds. Because more of them were the p kind, the hybrid orbitals in this case here should be more like p than s. Remember, this is the blending of atomic orbitals. They really like asking you to define hybridization. Try not to use the word hybrid. Oh, you're just making a hybrid model or whatever. You can mention, yeah, there's some math to it, but really it's this last part here. We are mixing our atomic orbitals. We're trading in our s's and p's that the carbon used to have. We're always going to get the same number. I traded in 4, I get 4 out, and I'm going to get maybe a blended orbital. Those blended orbitals, like I mentioned, are going to be intermediate in energy, and then we're going to see out of the math actually comes the better spatial arrangement, the bond angles of 109.5. So because these hybrid orbitals here are some character S, some character P, we're going to see it as one big lobe, one small lobe, and these ones here are also out of the map. Not only do I get 4 of them, the 4 of them actually do come out as the tetrahedral geometry. They actually plot it for you. Each of these blended orbitals here, maybe that's the long lobe, short lobe, another one here, long lobe, short lobe, like that. It's already bonded at that perfect 109.5. So carbon has already pre-blended its S and Ps, and then hydrogen can easily come along. Oh, I'd be happy to share with that one. I'd be happy to share with this one. And there we go. We actually get the tetrahedral methane. Carbon not only making 4 bonds, it promoted that electron up, but those 4 bonds here are identical, and they're at a bond angle that's actually better spatial arrangement, 109.5, better than the p orbitals that used to only be 90 degrees. Again, you don't need to repeat the math. Okay, I did a whole degree in chemistry. I didn't actually need to see the math, but basically that's the overall, the broad stroke that we're looking at. I trade in 4, I get 4, and then these orbitals here are somewhere intermediate in terms of energy. So let's just continue this thinking of hybridization. The model is kind of crazy because there's a lot of math behind the scenes. As we get to the backside, we're going to see that the questions on the section are not all that bad. So here we're going to start off with a new molecule here. We'll talk about ethene. Eth, as I mentioned, refers to 2 carbons. Meth was 1 carbon. The ene ending actually puts you in the family of what are called alkenes. An alkene is known to have a double bond between carbons. So again, if you know that sort of organic background, when you see C2H4, I would expect to see something like C double bond C. I always treat carbon, it should have the equivalent of 4 bonds. So I've used 1, 2. That means I have 2 extra arms. The other carbon here is also using 1, 2. It has 2 extra arms. I would expect the rest of them to be saturated. In organic chemistry, although the name comes from the carbon chain, the carbon part of the molecule, I'm going to imagine that hydrogen just sort of fills up the gaps. Hydrogen attaches to the ends of these molecules. And there we go. We actually have drawn the molecule without necessarily going through count the valence electrons, work your way outside to inside. You would get the same picture if you did that way. So for this molecule here, Vesper only does 1 center at a time. So in this case here, I actually have 2 carbon centers. Each carbon center actually has 3 electron domains. We have 1 domain holding the hydrogen, 1 domain this way, 1 domain this way. 3 domains, the molecular geometry actually ends up as trigonoplanar. So trigonoplanar here is at 120 degrees. Again, because this is dealing with carbon, I cannot take my S's and my P's. I'll actually redraw it on the other side here. I can't take my S's and P's. P's are at 90 degrees. I can't explain a bond angle of 120. Same problem over here. We get a 120 sort of orientation. So let me actually draw a little bit bigger on this side here. So on an energy level diagram, I have my 2s orbital. I have my 3p orbital just minding their own business. Carbon ground state looks like this. What we're going to do is, because carbon eventually will need 1, 2, 3 bonds to be made, I want to make 3 unpaired electrons ready for bonding. So same thing has to happen. I need to take an electron. I need to promote this electron up to a higher shell. Now you might be thinking here, well, I already have 4 unpaired electrons. I can actually make 4 bonds. In this case here, we know we need 3. We know that they're going to be somewhat similar to each other. But again, it can't just be these p orbitals, my atomic orbitals. It can't just be the orbitals that I currently have, because my atomic orbitals are all at 90 degrees from each other. So what I need to do is I need to do this hybridization. I'm going to sort of switch to the math here. I'm going to need to try to do a pre-blending of this molecule here. I cannot mix 3 p orbitals together because they already are alike. I'm not going to get the same thing out of it. What I need to blend is I need to blend in some S character. So what I'm going to do here is my hybridization. I'm just carbon. I haven't attached to other things yet. But for carbon, I'm going to trade in one s and two p orbitals. You should be able to tell me the name of the orbital is now called an sp2. Traded in one s and two p's. I traded in a total of 1, 2, 3 individual orbitals, so I should get 3 orbitals out of it, and those 3 are going to be somewhere intermediate in energy, somewhere in between the low shell and the high shell. So I have sp2, these are pre-blended of my own s and p orbitals. Those 3 electrons that used to be there are now ready in a trigonoplanar fashion. These blended orbitals will also have one long lobe, one short lobe, but this time because I've only blended in 2 p orbitals, I end up getting a nice trigonoplanar, a nice 120-degree relationship. So what I'm saying here is the carbon on the left side, see if I can color code it here, the carbon on the left side is using an sp2. Sure, it has a long lobe and a short lobe. There's going to be another long lobe and short lobe, long lobe, short lobe, long lobe or big lobe. Oops, sorry, let me do it the other way. Long lobe and a short lobe this way, right? So not only do I have these blended orbitals, the blended orbitals look identical to each other, you can't tell the difference. I also get that 120 degrees, where previously I was limited to that 90 degrees. Hydrogen again comes along perfect. I can bond to this side, I can bond to this side, I can explain what VSEPR predicts for you. In fact, this VSEPR is so successful, as we do our questions on the backside, we're going to actually do VSEPR, and then we're going to work our way backwards and say, oh, what hybridization did I need to match up to this VSEPR? Now, this is one important thing that comes out of this section here. So the carbon on the left side, it has a bunch of these hybrid orbitals here. Same thing on the carbon on the right side, also trigonoplanar, also 120. Because it's trigonoplanar, we can then say, let me see if I can color code it here. I can then say sp2 orbital, sp2 orbital. I'm just going to draw the long lobe because that's the lobe that actually does the bonding. And therefore, we have hydrogens attached. There's 2 trigonoplanar sort of relationships. The overall molecule so far is flat. What's interesting here is hybridization not only, I know there's a lot of math that's hidden in, hybridization predicts for us some of these bond angles, and it makes our VSEPR jive better with the SPDF. It actually gives us a new interpretation of what a bond is. So in my diagram, my Lewis picture, I had drawn a carbon double bonded with carbon. We know that bonds are made out of 2 electrons apiece. There's some electron density. It's attracted to the cores of the 2 carbon neighbors. We can actually realize with this formulation of it, because these orbitals here refer to electron overlap, there's electrons that are sitting in these blended orbitals. There's an electron here, there's an electron here. We can actually just focus on the orbital itself. We're going to actually give rise to 2 different types of bonds. In this case here, this is the stronger of the 2 types of bonds. I'm going to purposely point my red sp2 orbital directly head-to-head against the sp2 orbital. Wherever the electron orbitals overlap, that's actually where a bond exists. So in that case there, that type of bond there is referred to as a sigma bond. I have the definition down below. Make sure you know these definitions. They really like asking you, what is a sigma bond? This is a direct head-to-head overlap, and it's along something called the internuclear axis. If I imagine an axis, if I imagine a line that connects the internuclei, it comes between the 2 nuclei, you'll notice where it overlaps, it actually overlaps exactly over this arbitrary line. So sigma bond is the stronger one. It's very purposeful overlap because I want this one to be directly head-to-head against it. This one here makes it look like they're sort of far off. In reality here, the orbital is more like this diagram. The orbitals are overlapping. Wherever there's overlap, there's a bond. So far on my Lewis model, I know for a double bond, at least one of them is referred to as a sigma bond. That's the Greek letter sigma. It's like an O with the tail on it. Question here is, my Lewis also predicts, wait, there's actually a double bond. There's actually another bond to it. The question here is, well, with this electron orbital overlap forming bonds, I don't see how carbon can actually form that second bond. So far, carbon has hybridized its orbital. So far, it has 3 orbitals. Not only are the other orbitals already being used, the sp2 is holding hydrogens on the outside. You notice the bond angle. We were saying, the bond angle is actually 120 degrees. Those orbitals are pointed way away. They're totally in the wrong direction. There's no way those orbitals can somehow come back on themselves and overlap. See if you can see it for yourself here. Where might the other electron overlap be? If you said the unhybridized p orbital, you'd be correct. In this case here, so far we've blended in 3 orbitals. I notice that there's one orbital. I'm going to call it pz for a second here. This pz is actually an unhybridized orbital. This one here is actually the very same p orbital I had before. I didn't need to trade it in because I only needed to make 3 bonds. If I, for example, traded in my px and py, I may have lost the one on the x-axis, the y-axis. At least I have a pz that's up and down. I have a pz on the other one that's also up and down. So first thing is these are unhybridized. These were not in the blend. In this case here, again, the diagram is a little bit misleading because it looks like the carbon centers are really far apart. In reality, although yes, these orbitals here had no reason to overlap, right? They weren't trying to overlap, but because the two carbon centers here, if you actually look at the radii, you actually look at the bond length, you actually realize the carbons are actually a lot closer than they appear to be. So in this case here, finally, we have a new prediction here. Out of the hybridization actually comes a different type of bond. We have a sort of sideways overlap. The red and green just so happen to match up. The overlap above and below is referred to as one pi bond. So if I take the PZ on the red guy and the on the green guy, PZ this way, they were not purposely head-to-head. So instead, we're going to use an indirect sort of sideways relationship. In this case here, it's off the bond axis. This one here is not in between the two centers. That one there was a sigma bond. But like we mentioned, wherever there's electron overlap, there's going to be what's referred to as a bond. So in this case here, the PZ overlaps with PZ. The overlap above and below is just one pi bond. So make sure you do know those two definitions of what is a sigma bond, what is a pi bond here. These two are on the backside referred to as the molecular orbitals. It's like another layer of hybridizing. Basically, instead of just hybridizing just the red guy's orbitals or just the green guy's orbitals, I'm going to take your red orbital and your green orbital, and I'm going to come up with a bond that actually belongs to both of you. So it's just yet another layer of hybridization. So in this case here, we can predict anytime we have a double bond, one of them is the stronger sigma bond, that's in between the two centers, and one of them is the weaker pi bond. It's weaker because the overlap is not as significant. They weren't purposely pointed towards each other. In chapter 5, we're going to come back and look at bond enthalpies. Sure enough, having two bonds is going to be stronger than one, but we're going to find that the pi bond is energetically weaker because the sideways overlap is not as dramatic. So if you can flip to the backside here, we're going to study molecular orbital theory just in a little more detail in a later lesson, but just as it pertains while I have it here. So far we have, let's say, carbon. Carbon had orbitals like S's and P's, and what we did is we took those atomic orbitals and we pre-blended them. So when I did hybridization, so far my math, hybridization has come up with, I've done sp3, I've done sp2. But that has all been focusing on a single carbon. That's the blending, that's the math. Now, on the previous example that we just did, now I have a carbon on the left and a carbon on the right. I might actually have hybridized both of them. So sp3, sp2, and whatnot. Again, hybridization is defined sort of per atom one by one. And now what I did in the last example is I said, okay, what if I hybridize one more time? What if I take the red guy's sp2 and the green guy's sp2, and I actually hybridize these two, and now it becomes a sigma bond. Now your sigma bond, what I'm picturing here is carbon and carbon. Now I actually have a bond that refers to the overlap that would have been the sp2 overlapping the other sp2. I'm just drawing it as one single molecular orbital. I'm just drawing it as, oh, that's just a sigma attraction between the two bonds. And now through hybridizing again, we call it molecular orbitals. This is now an orbital that belongs to the entire molecule. Now the carbon on the left doesn't have an sp2 anymore. The carbon on the right doesn't have an sp2. They both together share the sigma bond. In a similar fashion here, we can actually use our unhybridized. We saw our PZ, we saw our PZ. I'm going to mix those two together. Again, it is a lot of math, a lot of pre-blending, the same pre-blending as I did for hybridization, but we're actually hybridizing not just one guy's orbitals, atomic orbitals by themselves. We're actually getting orbitals that belong to both of them. That actually became a pi bond. Pi bonds are always sort of like a banana-shaped bond here. That refers to overlap above and below. And now we have, that's one pi bond. That's the weaker of the two. It's sideways overlap. So I just want to show you just in general, we're not going to get in too much detail with molecular orbital theory, but just essentially it is hybridizing. Hybridizing so far was referring to just a single atom at a time. If I take the orbitals on the red side and the green side and hybridize once more, I would end up with these hybridals. A sigma and a pi bond is an example of a hybrid orbital, and those orbitals belong to both of them. For some reason in the curriculum, they always want you to know this name, although I have never seen any questions on it here. They shorthand it LaCow, and basically this is what I just mentioned. If you take your atomic orbitals, if you take the red guy's orbitals and the green guy's orbitals, so far you've just been hybridizing just red with red, green with green, separately. And what we do now is, because I want to add one extra layer of math, I want to hybridize the red guy's orbitals with the green guy's orbitals. What we end up doing is we end up doing what's called a linear combination. Essentially, for us to make a molecular orbital like a sigma bond, let's say I make a sigma 2s orbital, essentially you take the wave function, the red guys, maybe sp2 orbital, and I actually hybridize it with the green guys, sp2. Hybridization already happened for the red and for the green separately. My atomic orbitals have already been pre-blended, and now to make my molecular orbital, to make my sigma orbital for these electrons, is I'm actually going to pre-blend one more time. The linear combination aspect just means it's a simple plus or a simple minus. There's no squares involved or anything like that, and essentially we would just want to see a sigma is comprised of adding the wave functions of the red guys and the green guys together. I'll give you an example of this in a later lesson. We get bonding orbitals that are more stable, anti-bonding orbitals, even non-bonding orbitals. But again, we'll come back to this in a little bit later. So far, just based on hybridizing, it's hybridizing just on another layer. Last one here, because we're having so much fun with hybridizing, let's look at ethine. Eth again refers to it being 2 carbons. The Y and E ending actually tells you the carbon is actually triple bonded with carbon. So if I imagine drawing this picture here, C triple bond C, carbon has the equivalent of 4 bonds, 1, 2, 3, 4, 1, 2, 3, 4. That would then imply I should have a hydrogen on the ending of these. Now, to be sure, this one here, we actually don't need hybridizing. This one here, the VSEPR geometry around the carbon on the left is just linear. It's 180 degrees. If you look at just my regular old p orbitals, if I had, let's say, a px, and the other guy is also using his px, I can explain a 180 degrees no problem. But since we had so much fun with hybridizing, I'm still going to hybridize anyways. Here's what's going to happen. I have my 2s, I have my 2p. All of this is happening at energy level 2, so we have been a little bit sloppy. I don't really need to keep putting this 2 here. But what I want to do is I want to trade in my orbitals. I know however many I trade in is however many I get out. Because I want 2 orbitals out of it, I need to trade in 2 orbitals. They can't both be p orbitals, or else I'll just get the p orbitals back out. I'm going to trade in 2. I expect out of the math, out of the blending, to get 2 out of it. It's going to be intermediate in energy. It's going to be somewhere in between in energy, and I'm going to call those now sp orbitals. I traded in 1s and 1p, and surprise, surprise, in this case here, we get 1 long lobe, 1 short lobe, and that actually gives you that 180 degree relationship. S spherically symmetric, and the p is already 90 degrees apart. So in that case there we get a linear, hydrogen comes in here, bonds to this side, hydrogen comes in the other side, bonds to this side. Again, what we want to just use the lens of here is sigma and pi bonding. We want to see whether which one of these bonds are stronger or weaker or whatever. How is this orbital overlap actually explaining our bonds? So in this case here, we have an sp2 that's purposely pointed, I'll draw it on the side here. We have an sp2 that's purposely pointed towards another sp2. That overlap here is in between the 2 centers. We refer to that as a sigma molecular orbital. So at least one of these bonds here is a sigma. Where do the other bonds show up? Now in the previous example we were saying, oh, it's the unhybridized orbitals that actually do the bonding. I still had a py that actually wasn't used for bonding. Perhaps the py is up and down like this. The carbons look like they're very far apart, but these are actually going to overlap sideways. The overlap here is off the bond axis. Be careful, overlap above and below is just 1 pi bond, because this is just 1 p orbital. So far this overlap above and below is 1 pi bond. It's the second of the 2 bonds. See if you can see where the triple bond comes from. Hopefully you're able to say to me here, well, the p orbital here, I actually have an unhybridized pz as well. And with that pz, I'll try to color code it here. The pz is actually 90 degrees off from it. And what's going to happen is this is actually occurring in front and behind. So if I imagine in 3D again, having in front and behind ends up letting you overlap. In front and behind is yet another pi bond, and therefore a triple bond is made out of 2 pi bonds. So again, not only does hybridizing sort of fix our models, puts our models together, it makes us some good predictions. As I mentioned, the questions themselves are not too bad. We just saw sigma bonds. It's always the stronger of the 2 types. So sigma bond, single bond, every single bond is going to be the stronger the sigma bond. A double bond is comprised of 1 sigma, 1 pi, 1 strong, 1 weak. And a triple bond, just like we saw, one of them is a sigma that's in between the centers, and the other 2 are going to be pi bonds. So what's nice here is we can actually predict the hybridization for certain molecules. Again, you have to start off with the Lewis, because then we can identify the VSEPR. Because VSEPR is so easy, I just matched it up. If you are this VSEPR geometry, I'm just going to give you a table later on to actually match up which hybridization, which blend do we need. So in this case here, I can go up to each center one by one. This carbon here happens to need 2 orbitals. The VSEPR geometry is linear. So far we saw the blending that gave you linear was using sp orbitals. The carbon here is actually sp hybridized. Same thing with this nitrogen over here. Nitrogen is 1, 2. The nitrogen is also linear. Whenever we're linear, we just have to be sp hybridized. So as long as you memorize the shape and memorize the hybridization corresponding to it, this one here will also be an sp. Now nitrogen doesn't have anything attached to this side here, but it definitely still has to have an orbital, a region of space, a domain that actually holds the lone pair. We can talk about here again, carbon and nitrogen made a triple bond. We expect it to be 1 sigma and 1 pi bond. This one so far I've shown you is a sigma bond. The pi bond is going to be overlap above and below, maybe my py, and then my pz that's sort of in and out, in front and behind the axes. I know these drawings are getting a little crazy, but there you go. That's going to be the second of the 2 pi bonds. So sometimes they just ask you that. They just ask you go through, label the different hybridizations. Other times they might give you a molecule. Alanine is actually an amino acid. Amino acid is made out of amine functionality, a carboxyl functionality. We'll come back to this in our organic section. Sometimes they condense the carbon. CH3 actually implies carbon bonded to 3 other hydrogens. And all they're asking in this question is just do a quick count. How many sigmas and how many pi bonds are there? Remember, every time you have a single, it's sigma bond. So if I can just highlight for you here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. For a double bond here, one of them is a pi bond. This one here has 12 sigma bonds. I only get a pi bond when I start getting double bonds and triple bonds. A double bond, at least one of them is a pi bond. I only have one thing that's a double bond here, so I have 1 pi bond. So you see the questions are actually fairly simple, although the theory is a little bit crazy. Here's that table that I just mentioned here. We've been using the blend that I need for linear as sp. Back when we did ethene with double bond here, trigonal planar, I did sp2. I traded in 3 blends. Tetrahedral was the first example, sp3. Because the VSEPR was so easy, I would do VSEPR first, and knowing these shapes here, you can just quote, what blending did I need to actually give you that geometry there? Notice that this one here has to be the orbital geometry, the electron domain geometry. Let's say I was ammonia as an example here. I still need to have an electron domain that's set up in the tetrahedral geometry, even if I don't actually have something attached to it. So this one I see as tetrahedral, I check my table. Oh, tetrahedral means these ones here have to be sp3 orbitals, or you can say the nitrogen is sp3 hybridized. Now we did an exception with expanded octets here. Sometimes your central atom had more than 4. It could have 5 or 6, so these are already kind of crazy. In this case here, I had mentioned, well, what if I was row 3 and lower? What if I took my S's and my P's, and what if I somehow accessed the d orbitals for bonding? The d orbitals for now, as an atomic orbital, are inner. They shouldn't actually access for valence bonding. But here's what I'm going to do. Because I need 5 electron domains out of this, I'm going to trade in 5. I traded in 1 S, 3 P's, and 1 of the d orbitals. Each of the orbitals are going to be called an sp3d. And because I traded in 5, I'm going to end up with 5 sp3d orbitals. Careful, this 5 here doesn't refer to energy level. I might only be on energy level 3, but this 5 here refers to having 5 different of these orbitals. So trigonal bipyramidal sp3d. If I want the 6th one here, just by extension, octahedral, just go trade in 1 more d orbital. We call each of those orbitals an sp3d2. That's the hybridization. And if I trade in 6, I expect to get 6 out of it. I expect to get the octahedral geometry. So lots of math behind the scenes. We get this nice notion of a bond being electron orbital overlap. We get this layer of hybridizing to blend atomic orbitals, and that moves us into a little bit of molecular orbitals in a later lesson. Let me end off with one last example here. This was actually a bonus question on my first year final. We now know enough to actually solve this problem here. I'm going to give you a molecule here, CH2CCH2. This is the molecule here, propadiene. And my question is a little bit strange. My question here is going to be, is this molecule planar? Now, normally what we would do is we would do VSEPR around each center one by one. I'm just going to shortcut this a little bit here. C with 2 H's. Then I have the carbon in the middle. I'm going to color code it for you here. Then I have the carbon on this side here. Right. The organic chemistry here tries to lay out sort of left or right how this molecule is built up. We know carbon has supposed to have the equivalent of 4 bonds. If I'm no longer holding any other hydrogens, I would expect probably a double bond on this side, probably a double bond on this side here. So far that's my picture. When I did my Vesper, I would do one center at a time. That's exactly what I want to do this time, but I want to see that if I do the Vesper around any given center, is the whole molecule actually able to be flat, or is it twisted? So let's try it out here. The carbon on the left side, this black carbon here, we know it has 3 electron domains. The hybridization is sp2 because I know the shape is trigonoplanar. That part there is going to be a triangular flat shape. Same thing on the other side here. I have trading 3 electron domains. The bonding is supposed to be 120 degrees apart. This one here is also hybridized. This one here is also planar, flat, no problem. The trouble here is we actually have a carbon in the middle. This carbon over here is actually only sp hybridized. Because I can quote that as linear, you can check your table, it's only sp hybridized. So what I'm saying here is I know this part is flat, and I know this part here is flat. Oh, that means flat. Well, it's possible that for this red carbon, this middle carbon here, it's possible I may have actually twisted the carbon, that it's actually flat on one side and actually perpendicular on the other side. Would you be able to predict for me? Normally I wouldn't ask you whether the whole thing overall is planar, but in this example it's a nice molecule to look at. We're going to actually rely on our Lewis models here. We're going to actually use that sigma and pi bonding to explain our question. I know this carbon actually has a sigma bond and a pi bond on both sides. So let's just draw this out here. The carbon is using, this is the black one on the left side, sp2, sp2, sp2. The carbon in the middle, sure, it's just using its sp orbital. What type of bond is this one when the overlap is in between the two centers? Hopefully you were able to say to me sigma bond. So at least one of them is a sigma bond. Where does my second of the 2 bonds come in? I know it on our lesson to be a pi bond. The pi bond comes with a p orbital. Maybe I had a pz and a pz. Overlap above and below is 1 pi bond because that's just one single p orbital. Great. So I explained the double bond on the one side. On the other side here with the green, it's also sp2 hybridized. I have carbon, sp2, sp2, sp2. So that gives me my trigonoplanar. I'm ready to hold my other additional hydrogens. What type of bond is this one? Again, and it should be a sigma bond. Now the question here is, where might this very last pi bond show up? Now the problem here is the blue pi bond here, maybe it's already used as up and down axis. I'm already occupying this one here. I can't stay flat, and I can't have my p orbitals and also share it with them because they're already being shared. But what's fortunate for us here is for the carbon that's in the middle, that's only sp hybridized. It's traded in the first two. It actually has 2 unhybridized p orbitals. One of them may have been the blue py's that have been used already. The other one, if you can see it for yourself, it's actually going to be the in and out axis. This one here actually has a pz that's in front and behind. This carbon on the right side here says, sweet, I can just twist myself. I can actually rotate my plane. This will be a little bit easier if I can show it to you in the model kit. But imagine twisting this one here exactly 90 degrees. It's now going to be flat on the picture so that my p orbital is actually going to be also in and out. Now I'm going to have overlap almost like a triple bond. This overlap is in front and behind, but this one is only a double bond because I have a sigma and just one of these pi bonds here. So therefore, if you look at this one here, the carbon on the left side, I've sort of drawn as a sort of flat plane here. The carbon would actually be flat on one side with the carbon in the middle. And then on the other side here, we had twisted it. So this one here is actually going to be bonded to the next carbon. This one's going to be H and H like this. This molecule here is not flat. This side is sort of in front and behind. We looked at the p orbitals being vertical. The other p orbitals here are actually in and out of the plane here, and therefore the shape of the molecule is actually 90 degrees off from it. This is a slightly twisted molecule. Right? So practice a little bit of hybridizing, practice a little bit of defining sigma and pi bonding, and we'll go from there. Thanks, guys. Take care.